Welcome to this video on Introduction to GPU Architecture and Computing. My name is Jakob Lumjan. I'm a trainer with the Applied Parallel Computing Corporation. In recent times, GPUs have been finding a wider and wider array of utilization in different hardwares. At the bottom end, we have the Tegra carrying devices, such as smartphones and tablets. These allow for augmented reality for the user, and they also allow for autonomous robots and unmanned aircrafts. Put together, they can also constitute energy-efficient data centers. Moving upwards in performance and also in scale, we have the normal mobile workstations that you and I carry around every day. These usually contain some form of GeForce card, and this allows for general purpose GPU application development, but also for GPU accelerated CAD and CAE, for example. Moving further, we have the stationary GPU workstations. These allow for an even wider array of utilizations and applications of numerics. And it's also when we can start discussing using multiple GPUs in a single machine. If you need even more performance than that, we move up to GPU servers or clusters. At this point, it's almost certain that you have multiple GPUs in each server. And these allow for advanced technologies such as graphics virtualization or remote GPU computing. Also, it might be interesting to note that GPUs are also useful in providing information and entertainment for drivers, and as well as the passengers in automotive systems. So what does this look like in actuality? We're going to be looking at a node of the Titan cluster. So first off, we have the CPU and the memory that is tied to it, which is the host system, DRAM. Then we also have several GPUs. Now, what's important to note about these GPUs is that they carry their own DRAM. So this is going to change the way that we need to program with these devices in mind going forwards. These nodes are so-called fat nodes. They contain 4 GPUs per 2 CPU sockets. Now, depending on whether the I/O hub is unified or separate, this can be either a uniform memory access system or non-uniform. Different processes can make use of the same GPUs as well as utilize several GPUs. Similarly, this also applies for different threads inside of a process, which can be bound to several different GPUs, and these GPUs can also overlap. Underlying all of this are the GPU contexts, which allow us to utilize several GPUs with the same thread, as well as utilize the same GPU for different threads. Now, taking a look at the evolution of the GPU ecosystem, just going back a couple of years means that GPU computing was a technology for experts. Any GPU program that you wanted to write had to basically be written in CUDA. And this only worked on one specific GPU family. Now fast forward to just last year, and GPU computing has become a technology for everyone. There are a wide range of GPU-enabled libraries that implement all kinds of data processing, such as BLAS, Magma, cuSparse, AMGX, cuFFT, Thrust, Cub, etc. There are also directive-based languages that simplify GPU programming, such as OpenACC and HMPP. These are used when you want to provide some knowledge of the underlying architecture, but don't want to go all the way down to CUDA level. It also works on 5 generations of GPUs, all the way from the G80 generation of 2006 to the Kepler and Maxwell generations of today. CUDA is now something that you only need to be using if you're after something very specific, or if you're looking for the absolute highest performance possible. Going forward, there will be three levels of GPU application development that will be useful to consider. At the top level, we have black box utilization, where you use a library which accesses the GPU itself, and you don't particularly need to worry about any specifics using the GPU. Going forward, you have directive-based programming, for example, such as OpenACC. In this case, you need some degree of awareness of the GPU details, due to the fact that you need to give the compiler some advice on how to properly utilize the GPU. Moving further, we have CUDA, where you have to specifically designate for the GPU exactly how to perform all of its tasks. Now let's look at some examples. We'll start off with matrix-matrix multiplication on 4 different hardwares. These hardwares will be used throughout these examples, so I will only be discussing them this time. We have dual Xeon processors, as well as a Xeon Phi, a Radeon graphics card, as well as a Kepler K20X graphics card. In this example, they are all using different library implementations of this matrix multiplication. As you can see, the difference in performance is massive. Starting off, the CPU implementation simply calls the BLAS function for matrix-matrix multiplication. We can also see that the GPU code is slightly more bloated. It has the same component in the sense that it also calls a function of the library. In addition to this, however, we also need to allocate space on the device. We need to create the handle for the cuBLAS. We need to set the matrix in the device memory. This is copying over the information from the CPU to the GPU, or the CPU memory to the host GPU memory. Finally, we need to read the results back. Also, there is some boilerplate corresponding to freeing up memory. Now, this is worse in older versions of CUDA. For CUDA 6.0, the NV-BLAS library is introduced. This automatically routes all the standard BLAS 3 calls to cuBLAS by preloading a specific library. This can also spread work across multiple GPUs. And of course, it can be used with any application that calls BLAS 3 functions, such as Octave or Scilab. Another example that showcases the potential of Tesla K20X GPUs is that of sorting key value pairs. We're again utilizing the same hardware, but even compared to the previous example, the difference is greater. Again, we are using libraries for this. So in this case, we need to first generate the random keys and values on the host. These values need to be transferred to the device, and the sort command is simply a single line, after which you need to synchronize and copy the data back to the host. And this isn't even the end, because the recently released cub library from NV Research offers even 2.5 times higher performance than we have displayed here. In our next example, that of wave propagation stencils, we move down a layer in abstraction to the OpenACC directive-based programming model. As you can see in this example, the difference between a normal CPU implementation and the GPU implementation is simply that of adding 3 lines of pragmas, which explain to the compiler how to properly utilize the GPU in order to attain the required results. So as you can see, OpenACC allows for very simple yet still powerful offloading of computations to the GPU. The PGI OpenACC 14.1 compiler can often generate faster kernels than even handwritten CUDA, which you have spent a lot of time on. So what are the differences between CPUs and GPUs that allow us to gain such a huge advantage? In the original design philosophy, we have CPUs consisting of several complex cores, while GPUs have thousands of simple compute units. This is a difference in design philosophy. CPUs try to gain an advantage by utilizing things like simmed vectorization, which complicates the program slightly because you need to find certain patterns, while GPUs instead try to utilize the massive amount of scalar cores, which to some extent provides extra flexibility in the sense that your problem does not need to look like vectorization. Finally, CPUs utilize a lot of their chip for large caches in order to shorten the period of transferring from CPU memory to the CPU itself. Instead, the GPU decides to use a very large register file and shared memory. This allows for different threads to be swapped in and out of execution, which means that you can, at any time that the thread is waiting for its data, switch it out and instead execute another thread that has its data available. Also, the execution model is different between CPUs and GPUs. The notion of a thread is common to both the CPU and the GPU, but the CPU has processes consisting of one or several threads. Meanwhile, the kernel has a few more notions that are important, such as that of a warp, which consists currently of 32 threads. These warps are executed entirely in parallel. Warps together constitute blocks, and these blocks together make up the entire grid of a GPU kernel. On a CPU, the processes and threads are maintained by the OS, which means that they require quite some resources. The GPU design philosophy instead makes these threads very lightweight and are maintained by the GPU driver. Memory latency is relaxed by using the 3 levels of caches in CPUs. This takes up a lot of space on the chip. Meanwhile, the GPU utilizes active thread switching in order to hide this memory latency. So what are the patterns that we need to keep in mind in order to make our GPU application efficient? First off, there's a bonus. GPU computations are scalar, which means that we don't need to worry about the vectorization that is so present in CPU programming. First off, the GPU task has to be partitioned into significant amounts of small parallel tasks. This means that we need to have a significant amount of separate activities that can be performed entirely in parallel in order to fill up these GPU threads so that the model of switching out waiting threads is possible. We also have the 2 key resources of registers and shared memory, and the use of these must be balanced in order for us to be able to actually have all these threads running on the GPU at the same time. It's also very important to ensure that any memory accesses are coalesced, and we will be discussing what this means. Finally, it's very important to make sure that we do not have divergent if-else branching to as large an extent as is possible. So what happens if the amount of parallel tasks is too small? Well, we're going to be wasting compute resources due to the fact that there are no tasks to be allocated to them. It is not a problem if we have an excess of tasks, since this just means that we can first perform all the calculations for the previous tasks, and then finally allocate resources to the final task. Also, if we have an imbalance in the use of shared memory and registers, this again means that we will not be able to schedule properly on the GPU the tasks to be performed. This means again that we are wasting our compute resources. The final issue with regards to GPU efficiency that will be highlighted here is that of divergent if-else branching. In our left example here, we check for each thread if they are supposed to perform a certain piece of code. The threads that do not are just going to be occupying compute resources idle. This in itself is an efficiency problem, but it's even worse when we look at the right example. In this case, we still have the same check for whether our thread is supposed to perform the first piece of code, but also for the threads that do not, they have a separate piece of code afterwards. This means that even if you are performing the code at first and you are finished with that, you will still need to wait for the other threads in your warp in the else block to be finished. This is a major problem when it comes to efficiency. So what can we take away from this? Well, first off, if your application is suited for massively parallel computations, then GPUs will be able to offer you much higher performance than most reasonable alternatives on the market. You can also start using these GPUs rather easily. At this point, we have seamless integration into applications with existing parallelism, such as using MPI or OpenMP. We also have fairly efficient GPU-enabled libraries for a wide variety of computational problems at this point. And now, CUDA is only really needed when you need to develop something that is highly specific and not covered by these libraries, or something that is on the top of performance. That's something that you need to tune to the absolute peak performance. We need to keep this in mind though, that the GPU architecture and execution model are designed for massive parallelism, which means that your problem both needs to be suited for this, and we need to account for this in the programming process itself. This leads to the four main factors which decide GPU efficiency. First, we need to ascertain sufficient parallelism to make sure that we can actually utilize the entire device. We need to have a balanced use of registers and shared memory, again for the same reason, because we need to be able to utilize the entire device. We also need to have correct DRAM utilization in order to avoid coalescing misses, for example, and having the entire bandwidth. And finally, we need to minimize the amount of divergent branching that our threads are subject to in order to, again, properly utilize the computational power that the GPU grants us. Thank you for listening to this video.